Hi, I'm Goh Zee Xin. I'll do the demonstration for project 3. So project 3 requires me to design a n-stage ring oscillator using the NAND gate as the single buffer to activate the oscillation system. So first, I will show you my inverter design in terms of schematic and layout. So here I will first to open terminal, type with SID, and then here I will open my design. So this one is all of my design, and then I will show you my schematic design for the NAND gate. So this one is my design for the NAND gate. This one is the PMOS with 350 nanometer wide and 250 nanometer length. This one is also the PMOS. And then the bottom one is the NMOS with 350 nanometer wide and also 250 nanometer length. So this one is the design for the NAND gate. And this one is the input of A and B. And my output is Q. So this one is my output. So here I will click on cell, generate symbol, and then choose for this one. And the view I will need to type symbol, and then click on replace. So this one is my symbol generated. So here you can see input is A, and then the output is Q. So this one is my NAND gate simulated, and next I will use the symbol to do the simulation for NAND gate. So this one is my test bench for the NAND gate, and also need to note that this one is a 2-input NAND gate. So here I will use the pulse width to simulate it. So here we will set up first the simulation. Click on the simulation. So we'll click on the transient, and then aldo print interval 200. Print start time is 0 nanosecond, maximum time span is 1 nanosecond. And then for the general, I will insert the library file with the generate 250 model spice robot .library for different mode. And then I will run simulation. So this one is the simulation obtained. So we can see for the NAND gate 0, 1 is get 1, and then 1, 0 get 1, and 1, 1 getting 0. And for the 0, 0 we get 1. And so this one is the correct NAND gate simulation. And then next we will go to the LED to simulate for the layout of the NAND gate. And then I will go to the SDL to invoke the LED. So this one is my layout design for the NAND gate, and I will simulate the DRC. Since I already run previously for the decimal set, I'll click the decimal set and OK for the rules. And then run DRC. So since no result file means the DRC is completed and no error. Then we will run the LVS. So I'll choose the LVS run set previously, and then run LVS. This one I'm using schematic one. Run LVS. So here we can see the LVS report, and all the cell and the layout is the same, so the comparison result is correct. So this one is the report. And we can see also the LVS calibration report here. So before running PX, we will go to here to set up the variable. So the variable should be LVS path, and the value here is the default path. And then click OK. And then we will run the PX. So this one is my PX run set before. So I will click on it and run PX. This one is my output for the PX characteristic result. So no error found. So next we will proceed to the ring oscillator schematic design. So this one is my ring oscillator schematic design using 2-input NAND gate. So I have 5 2-input NAND gate. So it's the first, second, third, fourth, and the last 2-input NAND gate. And I will tie together the input of the 2-input NAND gate together and become an inverter. And then from here I will generate the symbol. So here I will click on ring oscillator and then symbol, and then click replace to generate the symbol. So this one is the ring oscillator symbol generated, and I will use the symbol to do the test batch. So this one is the symbol generated, and this one is my test bench. And the left one is the V1 and V2 is the reference voltage to let it oscillate itself. So here I will click on start simulation. So this one is my pre-layout simulation of the ring oscillator. So I can zoom here to get the waveform and then get the period. Also get the hold time and rise time. So from here, the period is around 748.05195 picosecond. So I'll calculate it and get the frequency. So the frequency is around 1.34 gigahertz. So it's meet the requirement of the project, which is exceed the 100 megahertz design. So at the schematic, I will click on the SDL to invoke the tunnel LED. So this one is my layout design. So the leftmost is the first NAND gate, second is the second NAND gate, third is the third NAND gate, fourth is the fourth NAND gate, and the last one is the fifth NAND gate. So I'm connecting the output together with the input. So the output of the previous NAND gate will be the input as the next NAND gate. And then for the output, I'm using the metal 2 to connect as horizontal and the metal 1 as connect in the vertical. Well, for the input, I'm using metal 1 to connect the horizontal and metal 2 to connect vertical. So at here, I will click on DRC. So this one is my result, which is no result found and means no error found. Next, I will proceed to the LVS. So this one is the LVS. And I might need to make sure the design is correct and the view name is correct. And then I will run the LVS. So this one is my LVS report. We can see the extraction result is correct and the comparison result is correct. So the cell comparison result is correct because the layout and the source is the same. So next I will proceed to the PEX. So this one is the PEX, and then I will run the PEX. So from here we can see the warning is 1 and the error is 0. So means the design is able to extract the parasitic data correctly. And then we can also calculate the area inside the layout, and then I will select all. And then click on add in and then area calculator. So at here we can see the area report. Then next I will exit the ring oscillator SDL design. I will simulate again for the test bench. So at here I will set the pre-layout. So I will set it, and then I will import the calibrate view. So at here I will place the cell at ring oscillator and then calibrate view, and then make sure it is PX netlist and then import. After that, I will change the design netlist at here to become the calibrate view, and then simulate again. So this one is the OS layout simulation waveform of the ring oscillator. So we can zoom it. So we can see this one is the waveform, and then we can also measure the period and also the rise time and fall time. So at here the period measure is around 2.28205 nanosecond. And then from the calculation, I will get around 438.2 megahertz frequency. And this one also meet the requirement, which is exceed 100 megahertz. Next, I will open my pre-layout design. Then I will overlap it. So we can see the green one is the post-layout waveform and the yellow one is the pre-layout waveform. So we can see the overlaption, and we can get to know pre-layout is faster than the post-layout. And next, we will proceed to the PVT analysis. So inside the PVT analysis, we will change the VDC to the VPWR. And inside the simulation setup, so for the PVT analysis, I will set the general without the generic. Then transient analysis maintain, and parameter swap. We use swap time is linear step. Start value negative 25, stop value 100, step is 25. And then swap variable VPWR, swap type list of value, and then list of 2.25, 2.5, and 2.75. And then the corner is use the variable generate 250 nanometer, and then we set TT, FF, SS, FS, and SF, and then we click on run simulation. So from here, we can see this one is the simulation for the pre-layout. So at here we can click on different temperature and different VPWR and also different corner to get the value we want. And then this one is the PVT simulation waveform of the post-layout design. It is a bit different with the pre-layout design. So we can also zoom in to see. So this one is the zoom in version, and then we can also hide the thing we don't want and finding the different temperature and then different PWI and also different corner to analyze. So that's all for my demonstration video, and thank you.